Ralph Greco.
Science rules.
Ralph Greco.
Inertia is a property of matter.
Ralph Greco.
The Science Guy.
Welcome back, physicists. Today we're going to take a look at some interesting optical features like this cat in the glass right here. Plus I am going to start out with a little magic show here. So let's take a little look at my video I made, a little magic trick I did today. Here you go. Two arrows pointing in the same direction, pitcher of water. Watch what happens when I slide the pitcher in front. Watch the bottom arrow. The bottom arrow now has switched direction, as you can see. And then of course I'll keep sliding it back. It goes back to its regular direction. Let's do that again. Come back. A little magic trick for you. Arrow switches direction, comes back, and it's back in the regular direction. So, what do you think? Can you explain that? Plus, can you also explain why there were two arrows at the bottom of the picture? I'm sure you will after this short video on refraction. So, refraction is when light changes direction when traveling from one medium to the other, and therefore there's a change in velocity or speed of the light. This is caused by how optically dense the light sees the material. So, optical density is considered to be what's called the index of refraction. So, as you see these little wavefronts come in, they see a material here, medium 2, which is more dense, they will bend towards the normal. And so the normal, as we always learned, is drawn perpendicular to the surface. So we look at the two materials, the two mediums. One, in my example, with the arrow was air, and one was water, and there was also glass. So that's a pretty complicated one. There were three materials, but you'll be able to handle that in no time. So what happens is, if you think of it, the best way to think of this is a soldier analogy. So I'm going to let Mr. Paul Anderson from Bozeman Physics explain the soldier analogy, and you should think of this all the time when you're trying to understand refraction. Here you go.
And so let's get to that analogy I was talking about a second ago. And so imagine we have a marching band that's all walking together. And so we're looking at the marching band, the trumpet players, and we're looking at them from above. And as they're marching, they're trying to keep the space between them the same. So to the person to your left or the person to your right, we want to keep that exactly the same. And so imagine that they're marching down a road. You can see that they're going to keep that spacing between them the same. But let's say that there's a bunch of sand in the road. And so what's going to happen to their speed as they enter into the sand? Well, the ones that enter into the sand first are going to slow down. But since they kept that distance between them the same, you can see that the angle at which we came in equals the angle at which we came out. So we don't see that refraction going on. But now let's set it up so they're marching in at an angle like this. And so they're marching across, let's say, a parking lot, and they're going to hit some sand as well. So what happens is as they come in, which one is going to start to slow down first? Well, it's going to be this one right here. They're still going to keep this distance between all of them the same. And so watch what happens as they enter into the sand. You can see they're bending like that. And so we're going from a medium where it's faster to one where it's slower. So if I put in that normal right here, what happened? This is our angle of incidence, so it's big. What happens to our angle of refraction? It's going to be small. In other words, it's approaching that normal. And so you always, when you're looking at problems with refraction, you want to imagine that marching band in your head and figure out which way it's going to go. So let's try that again. We've got a marching band now going through sand, and they're going to come out into an area where they go faster. So they're all going slow, but they're going in a straight line. Now which one's going to start to go faster first? Well, it's going to be this one right here. They're keeping the distance between them all the same, and so watch what happens now. So it's bending like that. And so if we put in that normal again, our angle is actually increasing. Our angle of refraction is going to be bigger.
So thank you, Mr. Anderson. There, you get a great example of a great explanation of how refraction works with soldiers. And so think of this all the time here, bending towards or away from the normal if you get stuck. So this is a cool one I found where ants will do the same thing. So the ants are following this direction across the smooth felt, and then they hit the green rough felt, and they change their angle, their speed changes, and you get refraction towards the normal. So refraction only occurs when it changes from one substance to the other. So the speed changes and therefore it bends. So when it's bending, going from less dense to more dense, it bends towards the normal. So the angle of incidence is greater than the angle of refraction. And this is air and water, like my little picture experiment I showed you. When it goes from more dense to less dense, it bends away from the normal. And so this time we're coming from the water and into the air. Notice my arrows show the direction. So the angle of incidence here is less than the angle of refraction because we're going into something more dense. Sorry, it's something less dense, and therefore it speeds up as it moves into the less dense material. So light along the normal bends in which direction? Well, if there's going along the normal, the angle of incidence is 0. Be careful, a lot of you got that wrong on the last quiz. The angle of incidence here is 0. Not 90 like a lot of you said. It's 0. The normal from the normal we're 0. So when we go along the normal, there is no refraction. So light does not bend when it enters the medium perpendicularly. However, it does slow down because it still sees the materials being more optically dense. So we've seen millions of examples. I'll just show you a few more. This is the most common one: a pencil or a spoon in a glass of water. You've seen people underwater. Notice how his head appears to be shifted, because this is in air and this is in water. So the light coming to our eye has two different speeds. Again, air and water. Here's the polar bear, head in the air, body in the water. This guy over here, you can see his head is completely refracted away from his body because his head's in the air, his body's underwater, so there's a difference in speed. And here you can see a duck, same thing. And this is a great one. Physics is fun. He has his head above the water, lower index of refraction, faster speed. This one was one of the most classic ones from like the 1960s when they first started filming these, of a girl in the swimming pool, and she's completely separated by the index of refraction and refraction itself. So the pencil is placed in the exact center. You get pretty much the straight on view. It doesn't diffract much, but it does get enlarged. And then as you change the angle and become more obliquely, you get more refraction. So this happens because the object slows down, and there's a mathematical relationship. It turns out that the speed is dependent upon how the index of refraction. So the new speed is v. The old speed is the speed of light, c, which is 3 times 10 to the 8th. And so the material determines how much it slows down. So indices of refraction go from air, which is the lowest, 1. You can't have anything lower than 1. So that's a little question on your notes there. The index of refraction cannot be lower than 1. And probably for us, two of the most natural substances, most common one is diamond. Diamond has the highest index of refraction. And therefore, you pretty much know why people buy diamonds, because of their brilliance. And when they're cut properly, the light gets stuck in a diamond because of this slowing down. How much does it slow down? We'll see in a second. So here comes a ray of light coming in. You can see substance Y has to be less dense because it's bending away. Substance Z has to be more dense. Here's some numbers for you. If you look at air towards the normal, because glass is more dense, goes back into water, it's less dense, away from the normal. Into diamond, the most dense, it bends way towards the normal. Cubic zirconium, it comes out and bends away from the normal. Notice how close it is to diamond. It's actually fake diamond, so you almost get the same brilliance, but not quite. And of course, you don't get the hardness. And then back into air in its original angle that it came in up here. So if you have to determine the actual speed of something in a new material, you just use n equals c over v. It's pretty straightforward. So n equals c over v, you just look on the reference table here. Here's our earth science reference table. Here's something off the internet with way more indices of refraction. And you can see diamond for us is definitely the highest index of refraction, and air is the lowest. There's nothing lower than air. You can't have an index of refraction lower than 1, because you can see the equation supports that. So what would be the speed of light in diamond? So I'll just do a quick one here for you. Tomorrow I'll do all the samples. So n for diamond, you just look it up here. Let's see, diamond 2.42. So you just put 2.42 equals the speed of light. That's on the front of the reference table. I hope you have it memorized by now. 3 times 10 to the 8th, 10 to the 8th meters per second. And v is the new speed, we don't know. Cross multiply, 2.42 times v equals 3 times 10 to the 8th. Divide that by 2.42, and v comes out to be 1.2 times 10 to the 8th meters per second. So you can see that the power of 10 is still 10 to the 8th. It doesn't slow down that much, but it does slow down enough that it can get trapped inside. And I didn't mention, water's up here too. So water speed of index refraction is 1.33, and this is how we get rainbows. It's kind of cool. We'll look at that later. So this guy in 1637 named Willibert Snell came up with a mathematical relationship between the speed of light in any material, and it's basically called Snell's law. So it's a relationship between the angle of incidence and the angle of refraction in any two substances. N1 sine theta 1 equals N2 sine theta 2. Pretty straightforward. So N1 is the first index of refraction, usually air, and theta 1 is the index of the angle that's incident, which is usually measured up here from the normal, always measured from the normal, sorry. And then index 2 is the new material. So again, here we'll take a look at, let Mr. Paul Anderson show you a beautiful sample on this, and then tomorrow I'll do our physics samples, but this one's really nice, so I'll let you watch this one right now.
Now let's quantify a little bit. So we're going to use Snell's law in a PHET simulation. Remember, the index of refraction times sine of the angle of incidence, how it comes in, equals the index of refraction on the other side. And so index of refraction, remember, is related to the velocity. And so the index of refraction goes up as the velocity decreases. So let's take a look at this. So we've got a laser light bouncing off the surface. And so you can see there's a lot of reflection going on, but a lot of that light is also going to be refracted on the surface. And so in this problem, if you know the angle at which it comes in, could you figure out the angle of refraction? You need Snell's law to do that. And so I'd write it out like this, and then let me look at what information I have. So I have the angle at which it's coming in, so that's a given. I also know in air the index of refraction is 1. I'm also given the index of refraction of the surface down here, the glass, is 1.5. And so what am I really trying to solve for? I want to figure out that angle of refraction, how it comes out. So that's going to be my theta 2. So I plug in what I know. So this is index of refraction of the light, the angle coming in, index of refraction of the glass, and this is the angle coming out. So I solve for that. Now I've got sine of theta 2 equals 0.577. So I have to take the inverse sine to figure out what that angle is going to be. And so I get around 35 degrees. And so you may want to pause the video and make sure that you get an answer that's similar to that. And now we could remove the question mark, and you can see that that angle is going to be at 35 degrees. Also, you can see it's less, and the reason it's less is we're going from an area where it's faster to an area where it's going to be slower. Now you could also have the problem presented like this. So in this problem, what am I giving you? I'm giving you the actual refraction. So it's coming in at an angle of 60 degrees. You can see that the angle of refraction is going to be 20 degrees. And so could you figure out the index of refraction? Same thing, we're going to use Snell's law, and now you just have that one known, or those three knowns, and the one unknown that we don't have is going to be N2. Now what's interesting is if we look at material...
Okay, so we'll learn how to solve one of those tomorrow in our Zoom session, not tomorrow, but whatever day it is, Tuesday. So thanks for listening, and hopefully you'll come to the Zoom session to learn how to do the sample problems.